Okay, so I think we can go ahead and get started, and I'm sure some more people will come in here in the next few minutes. So I want to thank you all for joining us, and I want to congratulate the pre-docs on completing the program successfully, especially during these difficult times. I regret I didn't get to meet any of you personally. Well, some of you, I think everyone was at the CCA. I'm not even sure. I haven't been there myself in many months, so it feels a bit weird. I do hope that you come back and visit us in more normal times, and I'll look forward to greeting you then. That would be great. You're most welcome to come back and give a lunch talk, or just come back and say hello. I think as David was walking home, I think that he's probably there by now, but David Spergel was going to say a few words.
So I just got back from getting my second COVID shot. So just got it on the Lower East Side. Advantages of having high blood pressure. Soon you'll all get your shots. But let me first begin by thanking both the mentors and the students. This has been an incredibly challenging few months, and we're so proud that you were able to accomplish what you did in this time, and really pleased and looking forward to hearing the talks about what everyone's done, and just really wanted to recognize people's perseverance, that this has been a very difficult time in many ways, and you have triumphed and gotten great science done. So looking forward to hearing the talks.
Thank you, David. So we can go ahead and get started. First up, we have Quadri Chance.
Hi, I'm Quadri. Over the past few months, I've been working with Dan using Gaia measurements to find unresolved binaries. Whoops. Okay, can everybody see now?
Yes.
Awesome. So there are probably a bunch of reasons why an astronomer would be interested in finding unresolved binaries. Mine centers around planet formation. So we know that from adaptive optics searches for companions, we know that there exists some limit for how close binaries can be before they start to disrupt planet formation. And we know that there exists another limit where they're far enough away where they don't suppress planet formation. What I'm interested in is in like the intermediate area where there should be some effect from a binary companion on forming planets, but it doesn't destroy the systems altogether. And so in order to do this investigation, you need to have like a pretty complete knowledge of what stars are and aren't binaries. That includes, planet hosts and non-planet hosts, but would be out of reach to be able to do that with an RV survey for thousands of stars. So we're using Gaia to do that. So to use Gaia, we assume that there's some distribution of RV noise, not the RV measurements themselves, because I think you get 6 to 10 RV measurements over like the span of say DR2, which is like a couple of years. It's not really enough to find binary. So we have to use, but we can use the noise properties to find binary. So if you assume there's some distribution of RV noise, and you assume that it's made up of 2 components, a Gaussian component, which represents like the noise floor for Gaia's RV measurements, and a log normal tail, which represents the noise that would be created by orbiting companions. If you assume that stars that are close in color and magnitude have similar RV errors, and therefore can use the same classification model, you bin them up into color mag bins, and then use a mixture model to identify the stars that are in the long tail of the RV jitter distribution in each bin. So most of that work was done a couple of years ago by Andy Casey, who I think was at the CCA for a bit. But most of the work that I've done, that I did while I was at the CCA, is surrounds, does this model actually work? And so the first hurdle in that is, do we recover simulated binaries? And the answer is yes. So I simulated 1 million binaries equally spaced in log mass ratio and log separation space. And you can see that, so on this plot, yellow would mean we're recovering more of the binaries in the bin. If we recovered every binary, the entire plot would be lit up yellow. You can see that we're actually like doing pretty well. We recover something like 60 to 70% of the binaries, and these are also evenly spread out in eccentricity and inclination space. So this would be like the first hurdle passed. The next would be, do we recover real life known binaries? So these two histograms are of all of the stars that we have RV errors for that pass our magnitude cutoff of 13th magnitude. But if we look at populations of stars where we know that they're binary, so in this case, the Kepler eclipsing binaries and spectroscopic binaries, you see that the probability of a single star, I should point this out now because it's to be repeated. We want 0 for this. This is the probability that the source is a single star. So the probability that these stars are single stars or are binary stars goes way up when we're looking at stars that we know are binaries, which is good. That's exactly what we want to see. The next hurdle would be, do we see the population features that we expect to see? So like large scale things. So again here, the color bar, yellow is what we want as a low probability of being a single star, so high probability of being a binary star. So this is just a color magnitude diagram. And you can see on top of the main sequence, we have a area where we have high probabilities of being binary, so the binary main sequence. And you can also see the increasing binary fraction as you go toward, as you go up in spectral type. So again, this is exactly what we expect to see. But all this is well and good. All of these tests showed that we're detecting at least some binaries, but we also need to know how many misclassifications can we expect to see. And the answer appears to be close to 0. So if you look here, these are all, 100th of a percent false positives rates. So at least along the axis where we're misclassifying single stars as binaries. Because the model is so conservative, there are plenty of binaries that will classify as single stars. And of course, this represents the idealized case. This comes from the simulated binary. So in real life, in real data, you have systematics and one-off events that will obviously make this false positive rate go up. So as far as what this can be used for, again, I study planets, so all of what I think it can be used for is centered around planets. So one possible use is exoplanet vetting. So here are all of the KOI stars that are flagged to varying degrees as possibly being binaries. So purple here is, we're pretty certain that this is a binary. And we get most of the false positive, which makes sense because most of these should be eclipsing binaries that are either grazing or diluted. So this would be like a good check to include in lots of different vetting codes, like Dave, for example, where they don't pass this check. even though something looks like a planet transit, like a diluted eclipsing binary, you can see in the RV that no, this should be a star. And another thing it could be used for is what I talked about at the beginning. So if you know what the binary rate is for planet host and non-planet host, you should be able to see, like, assign some suppression factor to binaries, and then get out the transit multiplicity that you would expect to see in like a Kepler survey. And this way we can actually test, like, if binarity suppresses compact systems, exactly how much it would suppress compact systems. I feel like I flew through that, but any questions?
Yeah, Lucia?
That's cool. I'm curious about at the very beginning, you said that you could assume that systems that had the same RV error like would be stars of the same magnitude. Could you elaborate on that?
Yeah. So I don't have the plot for it here, but we want to look at similar stars. So the baseline, like, RV jitter for a blue star or a giant or, you know, an M dwarf, they're all going to be different. So in order to try to get rid of that effect, we kind of just like grid them up. And so I guess we're assuming that stars that look like each other are actually like each other physically. But that's the point of gridding them up, is to try to get them among stars that should be the same-ish as them in reality. I can't see who was next. Kevin, I guess.
Yep.
Okay, very interesting stuff, Kadri. Could you please go to the color magnitude diagram that has the binary occurrence as a function of BP minus, yeah, that one. So this is saying that basically all F stars are not single stars. So the sun is at a BP RP of about 0.8.
Mhm.
And at 0.5, that is, let me see, what is 0.5 is basically an F3 star.
I'm unsure how exactly this is distributed within each bin. Whether there are a lot of stars that are here, like, in general, the stars are distributed pretty bimodally between either they're binary or not. But I don't know if that generalizes to here, because if it does, then what you're saying is right, that you should expect most F stars to be binary stars. So I guess the answer is I don't know.
Well, so it's definitely true that there are more binaries as you go to earlier spectral types, but the plot makes it seem like it's quite a strong gradient from the 0.8 BPRP of 0.8 where the sun is to BPRP of 0.5. So the sun, is it like the X is 0.8 and Y is like 4?
Mm-hmm. So right about here.
Yeah.
Yeah, I have absolutely no intuition for how strong that gradient should be.
Great. Well, thank you so much. Wonderful, wonderful talk.
Next, David.
So very nice talk and real nice work. Do you have a sense with the next data release how things will improve?
So this past one, I don't think had any updates to the RV parameters for any of the stars. But I think that's supposed to be coming with the R3. Does anybody know if that's actually true?
I think so, but I haven't kept track of what happens when with the data releases. I guess you get to go fainter.
Because your false
Yeah,
positive.
I think we'll be able to go fainter with more precise RVs, because right now, like 13th magnitude is about the limit for how deep we can go, and a lot of the Kepler planet hosts are fainter than 13th magnitude.
So you had, I guess, and maybe it was on the next slide, your false positive rates, which were pretty impressive, right? Which suggests maybe you can go fainter. You're willing to tolerate more false positives.
Yeah, I've definitely been thinking about that. Here, let me go back a bit, because you can see basically the false positive rate here. We have all of this space of binaries that we could say are binaries with no overlap with the distribution of single star RV jitters. But this is on like the very brightest end. And so we have the same thing here, but to less severe of a degree. We'll definitely be catching some that are singles, but I'll have to test to see like how aggressive we should be making the model and determining if stars are binaries or not. Because like the idea of like a super low false positive rate is really nice, right? So even as it stands, we say that stars that up to a 0.9 probability on this scale are probably binaries. So we have to see like where, like you said, where the trade-off is, where we're trading sensitivity for specificity.
Okay, great. Well, thank you very much, Kadri, for that very interesting talk. Next up, we have Sasha Chernoglasov.
So my name is Sasha Chernoglasov, and I was working here at CCA under Sasha Filippov's supervision with collaboration with Bartry Perdo, also postdoc here at CCA. So it was very, very useful for me to get there. And I'm going to talk about the relativistic decaying turbulence in MHD limit and how it can be applied to the astrophysics. So the astrophysical application is somebody who was listening to my talk at the beginning of the Pre-Doc program might remember this slide. I was talking that these astrophysical sources as pulsar wind nebulas, or like the remnants of supernovas, all these relativistic jets in other galaxies, they all have some very interesting non-thermal distribution of the radiation, or like the power law radiation, which as we believe comes from the synchrotron emission of very high relativistic, high energetic particles. And for the acceleration of these particles, we know that we have a huge pool of huge bath of energy, which is the magnetic field. But to get this actual parallel distribution of the particles, we need somehow to extract this energy very efficiently from the magnetic field and just to push it in the particles. And the actual reason for the motivation for my work is that there is a huge gap between the actual simulations which can be done at the modern time. Probably like in a few decades we'll be able to do a better job. The most accurate simulations can be done via so-called particle in cell simulation, where the particles are mimicked by the superparticles, just like a packets of particles, and everything, the Boltzmann equation and the distribution functions itself is evolved self-consistently. So we know everything, but this method, so like here on the left, it also shows some particle acceleration, for example, for this brilliant, very recent paper by Luca Camisa and Lorenzo Cironi at Columbia University. They showed that the particles actually get accelerated there, and they found some very nice power law. But this method has a very strong limitation to apply to the astrophysical sources, as it can simulate only like few hundreds of plasma skin depths at the best case. But the actual astrophysical sources just have 10 to the many degrees of this skin depth. And the other limit is the global MHD simulation, like shown here to the right. But unfortunately, we see that there is something interesting happens, like in this region where the energy is probably being pushed from the magnetic field to the particles. But the resolution here is like 10 or 50 points across the jet, and everything we want to study just disappears. So our idea was to consider this MHD simulation, which is very good approximation for very strong magnetic field astrophysical outflows. Even if the plasma here is the collisionless, we can approximate it with the fluid model. And just to consider like the periodic box simulation for this MHD, it was actually very interesting that this gap has been open for many decades, despite it's pretty obvious that it should be studied. And probably the reason for this is that this is the first time in our history when we can study this relativistic system with some just magnificent tool, which was developed by Bart. And we don't need to spend millions of hours just waiting while all these equations of resistive magnetohydrodynamics will be solved or will be evolved. And the reason why we care about, sorry, okay, yeah, let me just show you the video of like the turbulence. We just how it evolves in 2D cases. The 2D case is the easiest one. We can actually get the convergence and get the saturation of some physical parameters, which I'll be talking about a little bit later. So here we just steer the plasma with some magnetic fields, which have this like sine and cosine forms of just the waves. And what happens here, we just let it go. And we see that some small eddies create here, then they merge and like they keep going. But on the interface between them, there is something. This is the plot of the electric current. Sorry, I didn't say this. There are some interesting features here of this strong electric current, which can probably accelerate particles. So what is currents, the sheets of current, or the so-called current sheets are? So we just imagine that we have the magnetic field, which changes its direction, going from one side to another side. So this is just from the classical textbook. This is a plot from classical textbook. And here there is like a huge magnetic energy, but here at x equals 0, there is no magnetic energy. It all went to the particles or to the fluid. But at some ratio, like the thickness of the sheet, we can get the magnetic islands. Let me just show you the video, which was also simulated. So at the high resolution for the numerical simulations, because we need some pretty thin current sheets, we can get these magnetic islands, or it slides from particle and cell simulations is shown here. And you can see that the magnetic fields stored in these magnetic islands, also called plasmoids, is really huge. And these plasmoids can be considered as capacitors, which just take the magnetic field energy and put it pretty close to the speed of light. As it can be seen in this video, they move pretty quickly. Can be just delivered outside of the system at larger distances, and there, if they dissipate there, they will just accelerate particles which shine at the big distances from the active region, like close to the black hole, if we talk about relativistic jets or about accretion disks. And here is the example of very high resolution simulation, which was done at CCA, thanks to the supercomputer Papaya. In the converged state already, we can see that this is the electric current again. We see this a lot of nice features which merge. And the interface of them, these current sheets, I just zoomed this region here to the right. It has these fully developed chains of plasmoids, which are moving outside. You can see here like the plasmoid escaping this current sheet. And here they are also just propagating outwards and move out. And what, just to talk about a little bit about this regime, and it's probably also interesting for the amplification of the magnetic field and creation of the large-scale magnetic field in disks or so. The inverse cascade, when these edges merge with each other, can be pretty clearly seen. So at t equals 1, when we have the most developed spectrum, we have a lot of these small edges, but then they all merge and just only like few left. at t equals infinity, like only 2 edges left. Also, the same behavior can be seen in 3D, and it was shown pretty recently by Mooney. But I'll move further and talk a little bit about the statistics, what can be studied here. All this turbulent structure has some very nice spectrum which can be derived theoretically. And there was a recent idea by Bolderev that the actual edges, like here, like it's shown here, they change their shape going from scale to scale. So the ratio of the length over width or the width over length can be described as some function which scales like r over 1/4. And here I show the video demonstrating that the actual functions converges to these theoretical predictions pretty well. Okay, probably I don't have enough time to talk about this, and I'll just go to the current sheets in 3D as the actual world is 3D, unfortunately, as the simulations gets very expensive. So we have the same structure of we just steer plasma again with the magnetic field and Bx and By, also called in plane magnetic field, and we are having pretty strong out of plane magnetic field of the guiding field. The importance of the guiding field can be shown here as for the weak guiding field, which goes along the z direction, vertical direction here. These current structures, which are bright blue and red blobs or strains, actually deviates a little bit from the vertical axis, and here they are well better organized or structured. But in this out perpendicular to the guiding field plane, you can see some edges, which is pretty similar to what we have in 2D simulations. And here I just want to show you how these plasmoids, this is probably the highest resolution ever simulation of the relativistic turbulence with resistive MHD at least. Here you can see the example of some successful current sheet, which develops like a few plasmoids. This is in 3D again. And just to give you some feeling what's going on in this turbulent box, I'm just presenting a lot of slices at different Zs, and we are moving from one slice to another one. And almost at each time, you can see that the current sheets are being disrupted by like small structures which contain the magnetic field. And here, these edges here are just the initial perturbations, but at later t, unfortunately, the simulation isn't over yet. At later t, these initial conditions just disappear, but these intermittent current sheets, like these structures, are still in the system. So this is pretty nice. We can create a lot of current sheets. We can accelerate particles there. We can dissipate energy there. And here's the example. Here's the example of the current sheet, like one of the current sheets which we have in the simulation. Is probably the best one because it's isolated and it doesn't mess with other current sheets, which is stretched along the y direction. And you can just this red and blue plot below is the direction of By, which is probably like the reconnected magnetic field. And you can see that it changes its direction. So this is the actual reconnection. And here, like I highlighted 3 plasmoids, which also look like the flux tube, and the magnetic field lines are being wrapped around these electric current tubes, as the electric current is just the curl of magnetic field. And here we potentially store energy there. And if we just let this plasmoid go outside, we actually have a capacitor moving out and probably dissipates at some other points. And if we talk about the statistics, here it's a little bit more difficult, and actually nobody studied it in the full MHD. That the alignment is a little bit worse, this change of the shapes of the edge, but probably it's because it's a little bit more complicated to measure the size of the edges in the perpendicular to the guiding field directions. The guiding field also fluctuates a little bit, and the perpendicular plane also changes. But we can see here that while the spectrum is being developed, this alignment is approaching the theoretical 1/4. So this is pretty interesting result, is this 1/4 was developed in some very theoretical approach with a lot of assumptions, and definitely non-relativistic limit. But even the relativistic limit, the special relativity here approaches the analytical solution. And the spectrum is getting is being developed, so it's getting flatter and flatter, and probably at later t. I hope the simulation would be over by the moment of my talk, but I need to wait another couple hours before the results will be ready. It's getting less and less steeper, and probably approaches -3 hours as the theoretical prediction. But we need to wait to find it out. So, and here, yeah, just the comparison of the alignment in 2D and 3D. And you can see that they both are already pretty close, at least at some small r, the small size of the edge is pretty close to the theoretical 1/4. And hopefully it will get like close to 1/4 at larger separations if we evolve it a little bit longer. So, and this is the end of my talk, and I think I'm pretty close to the limit. So the challenges, I just end up with the challenges of 3D and what can be done for it. Hopefully we can try to go to the higher resolution, but it's more complicated to do, even as we're still far enough from the convergence and we can't employ the adaptive mesh refinement, which actually speeds up the simulations, especially in 2D. It did a very good job speeding up by a factor of 4. This is the part of the talk I skipped. So this is everything I wanted to say. Thank you.
Thank you very much, Sasha. Do we have any questions?
Sorry, I can't see anybody now.
Yeah,
Okay.
Alex.
Hey, great talk, Sasha.
Thanks,
This is actually a follow-up to a question I asked you a few months ago before a lot of these simulations had finished. But so you made a point earlier in the talk about the inverse cascade, but also you showed these amazing pictures from, you said maybe the highest resolution ever. So I'm curious, because of the inverse cascade and this turbulence, how much does the resolution really matter for the statistics you get out in the end because of this inverse cascade?
I think here's probably the answer to your question. If the mesh refinement part, which I unfortunately skipped, but you can see here that the mesh refinement IMR simulations represent the spectrum. This turbulence is probably the most important parameter pretty well at any moment. We really have about 60% of the domain living on the highest resolution at the most developed cascade. When the inverse cascade starts working, we just lose the amount of blocks living on the high resolution. So at the later t, we actually don't need this high resolution. But already this is for 32,000 square, if you remember, I probably advertised it already. But for the 64, we just doubled the resolution and ran it again. The spectrum is exactly the same. So we did resolve this, the end of the inertial range, which is dictated by not by the resolution already, but by the actual resistive scale, as this is the resistive hydrodynamics, MHD, magnetic hydrodynamics.
Great, thanks.
Drummond?
Awesome stuff, Sasha.
Thank you.
I'm curious about the difference between the weak guide field and the strong guide field simulations. What you showed at the end, yeah, exactly. What you showed at the end, I think, was mostly for the strong guide field. The results on, for example, the eddy shape. Do you see similar plasmoids in the weak guide field case? And also, how strong is strong for the strong guide field?
Okay, so it's like a few questions, which is actually, I thought about this a lot. When we drive, this is a decaying turbulence. It's pretty difficult to drive the highly magnetized simulations. They're pretty difficult to drive the magnetic energy there, since we just get the extra heating. If we leave it go for a pretty long time, just the perturbation of the magnetic field or the in-plane magnetic field decays, and this ratio of the guiding field versus perturbation field, or vice versa. So the perturbation field over the guiding field is slightly going to 0. It does reach some kind of saturation, but in the end, we do have this strong guiding field regime. This simulation here is done for weak guiding field, actually. as what we found from 2D simulations, that the plasmoids and the current sheets and the plasmoid chains look exactly the same at low and high guiding field. But the onset of this plasmoid instability is later for the larger magnetic field. So we just like made some kind of trick here just to save the computational and the physical time and study the plasmoids technically almost immediately. And sorry, I probably forget your third question.
No, that's perfect. That's exactly what I wanted to know. That's great.
Okay.
Thank you.
Well, hello everyone. It's great to see you guys again, even if it's just virtual. Today I'll be talking about some of the work I did at CCA with Adam and Matteo on stellar evolution in AGN disks. Actually, I'm going to try to make your box smaller so you guys aren't in the way of the slides. So how do stars end up in disks in the first place? So in quiescent stages, most galaxies are observed to have nuclear star clusters. And when these galaxies are in active phases, these stars can get trapped into the disk by gas drag or by exciting density or bending waves in the disk, both of which can act to bring these stars onto approximately circular orbits in roughly the midplane of the disk. Additionally, accretion disks tend to be gravitationally unstable at large radii, and this is just the classic tumor instability of self-gravitating gaseous disks. And if the cooling timescale in these disks is short enough, then this instability can result in star formation as opposed to just exciting waves. So now that we have stars inside the accretion disk, what actually happens to them, right? So the key difference between accretion disks and just the typical ISM to leading order is just that they're so much denser. So the Bondi accretion rate onto these stars can be extremely large. So recall the Bondi radius is roughly where the escape velocity of gas from the star is comparable to the thermal velocity of that gas. And this radius is proportional to the mass of the star and is typically a few orders of magnitude larger than the radius of the star. Now, just from continuity, the accretion rate onto the star is given by, it scales as this radius squared times the density of the gas. So it increases rapidly with the mass of the star and the density of the accreting gas. So eventually, as these stars are in this dense gas environment, they can accrete very rapidly and reach high masses. But once these stars reach high masses, their luminosity also just increases to very near the Eddington limit, at which point this radiation can impinge on accreting material and decrease the accretion rate, which we've implemented in MESA sort of as so. Additionally, once these stars are practically ripping themselves apart with radiation forces, this can drive super Eddington winds, which we've also parameterized in MESA. And now putting all this together, we have a decent picture of just how sort of spherically symmetric stellar evolution in AGN disks can occur. And note that for very low densities, evolution doesn't change too much from stars in the typical ISM. Here, the accretion timescales are longer than, say, the main sequence lifetimes of the stars, so not much changes. However, if the density of gas and the accretion rate is larger, then more interesting things can happen. So the first case I'll look at is the so-called intermediate regime of stellar evolution in AGN disks. And for reference, all these stellar models are starting with a 1 solar mass star, and they're just accreting a hydrogen-helium mixture. Now, this case is intermediate. In these cases, the nuclear burning timescale is comparable, but shorter than the sort of accretion timescales. So even though the stars accrete a lot of mass, they continue to chemically evolve. And the evolution of one of these stars is sketched out in the plots to the right. So in the top panel is just a Kippenhahn diagram with the mass coordinate of the star on the y-axis and the stellar age on the x-axis. Then the color is showing the helium mass fraction in the star, and the blue hatched regions are just showing where it's convective. Then the middle panel is just the cumulative accreted and lost mass from the star over time, and the bottom panel is showing the core mass fractions. So, this model started a bit into the evolution. It's a few solar masses initially. It has a convective core. It's largely burning CNO. And as it accretes fresh material, eventually the core expands and the convective region in the star expands and starts mixing in this fresh accreted material. And we can see sort of in the bottom and top panels, this temporarily rejuvenates the core and decreases the helium mass fraction. On the other hand, because the nuclear burning timescale is short enough, even as the star is accreting up to 50 or so solar masses, the hydrogen mass fraction after that initial rejuvenation just continues to decrease. And the star eventually runs out of hydrogen in its core and becomes pure helium. And then as it's around the Eddington limit, the accretion rate decreases to practically zero. And the star begins driving these super Eddington winds and decreasing in mass. But now, because the star is continuing to evolve chemically, even though it's losing mass, which decreases its luminosity relative to Eddington, it's also evolving chemically, which drives the luminosity upwards. So even as it's decreasing, it stays near the Eddington limit until it ends up around 10 or so solar masses, at which point we expect it to eventually leave behind a compact object or something. Now, this balance between the accretion rate and mass loss rate and the nuclear burning timescales is fairly delicate. If we increase the ambient density of the gas accreting onto the stars, we get what we refer to as the immortal regime of stellar evolution. And in these cases, the accretion timescale is short enough that the nuclear burning timescale is just too long for the star to actually evolve chemically. So here we can see the star eventually gets to a few hundred solar masses and becomes just fully convective, at which point it's able to rapidly mix all of this accreted material into the core. And we can see in the bottom panel that once it reaches this fully convective high mass state, the mass fractions in the core cease to evolve. Then from the middle panel, we can just see that over time, mass loss and accretion are balancing each other. And the star isn't perfectly in a steady state, but in an average sense it is. And it can eventually process many more times its actual mass, just from this mass loss and accretion, pumping out chemically enriched material into the disk. Now, the stars can stay this way until the conditions for accretion change. So the stars might migrate through the disk similar to planets in a protoplanetary disk, which could change the accretion rate onto them. And AGN disks have finite lifetimes, so eventually that could reduce the accretion rate and they could find a fate similar to the intermediate stars. But all of this so far has been sort of spherically symmetric Bondi-like. And one neat feature of AGN disks is that they tend not to be spherically symmetric. So once the stars get massive, other factors come into play. And that is what I spent a good portion of my time at CCA thinking about, is what happens when the Bondi radius of these stars gets large, comparable to other length scales in the accretion disk. So one of these, if you take a sort of standard equation of state for the disk structure, is that as you move away from the disk midplane, the density decreases. So once the Bondi radius is large compared to the disk scale height, then the sort of average density accreting onto the star is lower than when the Bondi radius was smaller and densities were closer to the midplane. Additionally, as the Bondi radius gets larger, the differential rotation of the roughly Keplerian accretion disk begins to matter, and this can slightly decrease the accretion rate onto the star as well. What we found to be most significant, actually, is the fact that the stars aren't in this accretion disk alone. There's another gravitating body in the disk, the supermassive black hole. So once the Bondi radius becomes large enough, the gravity of the supermassive black hole actually completely dominates the motion of gas at the Bondi radius. So instead, only gas that's within the Hill radius of the star, its rough region of gravitational influence, can actually accrete onto the star. And implementing all of these in MESA, I have the following just mass versus time tracks for various accretion prescriptions at various densities. So here the different colors are showing the different densities that are of the gas that's accreting onto these stars. So lighter colors are lower density, darker colors are higher density, and these are just CGS units. The little stars are just showing where the star undergoes a supernova, reaches the end of its life. And the top row here is just the sort of spherically symmetric Bondi-like prescriptions before. And then the middle panel is showing the effect of these tides on the evolution of the disk and the star in the disk. And then the bottom panel is just showing the effect of this vertical stratification of the disk. And you can see just overall that the tidal effects end up being the most significant, both in terms of what the maximum masses reached by these stars are and where the sort of intermediate immortal transition is. And a convenient thing about tidal effects actually is they really only depend on the star and where the supermassive black hole is. And this can neatly be parameterized actually in terms of the angular velocity of the star's orbit around the supermassive black hole. So with this, we can actually sweep just a couple of parameters to really map out the outcomes of stellar evolution in AGN disks based on just the angular velocity of their orbit and really the density divided by the sound speed to the third, but these are all at a constant sound speed for the gas. So here on the left is shown just the maximum mass of a bunch of these models, and on the right is the final mass reached by the models. And just looking at the final mass, or sorry, looking at the maximum masses for a moment, I've also just indicated where stars reach 8 solar masses. So this is roughly where we'd expect these to end up as compact objects and have some sort of supernova given enough time. Then looking at the final masses, because all the intermediate stars end up around 10 or so solar masses, it's really easy to pick out where the transition between immortal and intermediate stars is in this plot. And then additionally, I've marked some contours showing how long it takes the stars to reach this stage. So 10 to the 8 and 10 to the 7 years. And the key reason this matters is that AGN disks have finite lifetimes. So if the lifetime of the disk is shorter than how long it takes these stars to evolve this way, then the stars might not actually get a chance to complete their evolution. Now, on the other hand, since the Bondi accretion timescale is inversely proportional to the stellar mass, if you start with a star that's twice as massive, then the time it takes the stars to reach their fate is halved. Now, connecting this to some observations, one that I find really interesting are just these CRTS light curves of AGN. So we can see the typical AGN variability, and then every once in a while, there are these rare, gigantic flares that are just completely outshining the typical AGN variability. And one possible cause of some of these flares, and there was a wide variety of durations and magnitudes and whatnot, but some of them can be explained by supernova going off in these AGN disks. And additionally, as I mentioned before, we expect some of these stars to be rapidly rotating because they're accreting gas with non-negligible angular momentum. So we can expect GRBs, and this is something that Adam and Rosalba have worked a lot on recently. As far as another outcome of stellar evolution, it's nice to look at the mass loss rates from these models. Now, here on the left is the total mass loss rate from these stars averaged over their lives. And on the right is just the mass loss rate in terms of metals, or particularly just the carbon, nitrogen, and oxygen content. So on the left, we can see that the mass loss rate roughly matches the accretion rate, especially for the immortal stars, where they sort of match each other forever until something changes. And in these cases, if this mass is escaping at something like the escape speed from the star, then at the Hill radius, just the ram pressure from these outflows can be comparable or even greater than the ambient pressure in the AGN disks. So these can actually have a potentially important effect on the structure of the accretion disk even, depending on how many of these stars there are. Looking at the metals, on the other hand, because the immortal stars end up burning primarily just hydrogen into helium on the CNO cycle, they don't actually produce too many metals that are then sent out into the disk. On the other hand, the intermediate stars, because they progress to later stages of burning as they're losing mass rapidly, end up pumping out a ton of metals into the disk to enrich its metallicity. Then also those stars will eventually undergo a supernova, which can further enrich the metallicity in the accretion disk. And this just sort of generally ties into observations of AGN metallicity, where AGN are typically observed to have higher metallicity than their host galaxies. And this is just a plot from one particular study that looked at the metallicity evolution of broadline regions in quasars over redshift. And they found that the metallicity of the broadline regions was largely independent of redshift, but had a strong correlation with the mass of the supermassive black hole. And one possible contribution to this metallicity in these broadline regions is mass loss and supernovae from these stars in AGN disks. And with that, I'd like to take any questions. Thank you.
Thank you very much, Alex, for this very interesting talk. So I'll ask the first question. So people like Danielle Angles-Alcazar have looked at how stellar feedback affects feeding of black holes on sort of larger scales with galaxy zoom-in simulations. And so when listening to your talk, that's sort of what my mind jumped to immediately, is that these stars formed in situ in the disk could potentially have important implications for the accretion disk and for fueling of the black hole. And you talked about that a little bit at the end, and I'm wondering if you have any ideas and if you've thought about trying to simulate this effect with sort of a live disk and incorporating the stellar evolution and simulate it. I mean, to me, that sounds incredibly complicated, but I don't know, just interested in your thoughts about that.
So that's something I'm very excited about. I hope that in the future, this problem gets tackled as far as really accounting for the effects these stars have on the disks themselves. I know previously, something I've worked on before coming to CCA was sort of taking older disk models that, so Thomson, Quadrant, and Murray specifically, which sort of parameterizes stellar feedback as just the radiation pressure. Usually it's applied also to starburst galaxies. And in that context, I looked at how eventually the stars could reach the end of their lives. And I made a ton of assumptions about stellar evolution that are now being tested a little in more detail here. But what I looked at before was just how you could feed the supermassive black hole at, if you say, faster than the Eddington limit, just by eventually driving mergers with black holes formed in the disk, as opposed to just gas. But I think that with work such as this and other stuff that we're working on with Adam, Matteo, others, that we're getting closer to being able to really figure out how these stars interact with accretion disks they're in and around.
Yeah, hi, I'm Shashan, and thanks for having me here today. Just, wow, can I just talk about the research project that I've been doing in the Pre-Doc program, which is about this multi-phase galactic outflow that's driven by plasma phase. So galactic outflows are very important for us to understand galaxy evolution, and they are also being thought as an important part for star formation feedback. And observations are telling us they are not simply composited, but multi-phase gas with fairly complex structure. So I'm putting this schematic plot here, not to show the detail, but just to have an impression of they can have fairly complex structure that extend few tens of kiloparsecs away from the starbursting core. So it is important for us to understand them. And one of the famous questions related to this multi-phase outflow is, how do they actually form? Like, what is the source of this multi-phase outflow? So loosely speaking, people think there are two main categories that drives this outflow from star forming region. So first, they could be thermal source, which usually refers to the supernova explosions and the hot wind produced in the process, or it could be non-thermal source, which are what I primarily study. For example, it could be radiation pressure from all these young stars, and they exert on dusty gas and drive this sort of molecular outflow, or it could be cosmic rays, which I've been studying probably in past 1 year. And they are probably the more mysterious components in the energy source in the ISM, because we don't have direct extragalactic observation on them. But they could be an important energy source, even in our own galaxy. You could imagine they can take a good fraction of energy partition in some more star formation active galaxies. So people are doing simulations at all different scales, trying to understand the formation of this galactic outflow, from simulating the whole galaxy disk by inserting all these feedback mechanism and some subgrid treatment to only simulating some of interaction between this little small scale cloud and the feedback mechanism. So here are two examples that we did before. Like in this one, we are simulating a molecular cloud that's sitting in a hot background and interact with the incoming radiation flux. And we could sort of see that the cloud is getting disrupted. Some of the gas are being expelled from the cloud and mixing with the hot background. Some of the gas are still staying cold and molecular temperature. And this particular one was done in a frame that's centered on the mass center of this cloud. So it looks like they're not moving, but it's because we're boosting our frame every time step. So actually the cloud has flying somewhat distance away from the original position. And in this lower movie, I'm showing another example with similar setup, and now this time is accelerated by cosmic rays. So this type of small-scale simulations with a pretty well-controlled initialization and kind of idealized setup are very useful for us to isolating the physical process and resolve any potential small-scale turbulence and dynamic instabilities. But when we were looking at the cosmic ray interaction with cloud, we kind of have the impression that things could get more complex. It's now magnetic field is involved here. And by looking at a suite of these small-scale simulations, we got the impression that the topology of field could be somewhat sensitive to the shape of the cloud you put here. So I started to wonder how exactly should we interpret the result from such small-scale simulations with the kind of artificial initialization of this spherical cloud. And in other words, are they complex enough to directly interpret the interaction between cosmic ray and multi-phase gas in a more realistic galactic environment? So in other words, what can we do to go slightly beyond this spherical cloud? So this is another little test run we did with CCA cluster. I feel guilty for that, but don't ask. So one way to form a multi-phase gas spontaneously in the ISM is actually via thermal instability. So in this project, we did a set of pre-initialization run where we put a uniform slab and that in thermal equilibrium, perturb it a little bit and let thermal instability take over to spontaneously form a multi-phase gas. Like in this example shows the initialization of our fiducial run. Here are the result formed from thermal instability. So the upper panel is showing the gas density, while the lower panel is showing the gas temperature. So now we have some naturally formed cold dense gas that's sitting in a relatively hot and diffuse background. And we're running this to about 300 cooling time where it roughly reaches the steady state. And from this point, we inject the cosmic rays and watch the interaction between it and this spontaneously formed cloud. So in this project, there are three main questions we want to stress. The first two are probably relatively classic. So first, will cosmic ray be able to accelerate this gas to roughly the observed speed, which is about a few hundred kilometers per second? And second, for your gas getting that velocity, do you still have some cold gas? So can this cold gas survive during the acceleration by cosmic ray? I think a slightly new insight we should add to this problem regarding some recent work actually happening here is trying to put this mixing and cooling process into a framework of radiative mixing layers. So I think we should try to understand how do mixing and cooling actually happens in this process. And the last, probably the, excuse me, the most obvious one, what is cosmic rays' role in the process in terms of momentum source and energy source? And interestingly, how does that compare to hot wind? Because people think they are both originated from supernova explosions. Next, I'm just gonna play a little movie from our fiducial run where the upper panel is showing the gas density when accelerated by cosmic ray, and the lower panel shows the gas density accelerated by a hot wind with similar moment loading. And you would notice we're using the same initialization for both cosmic ray and the hot wind. So the first stage, all these little clouds, they're gonna merge into a fairly big clump. And after this merging stage, and they just kind of get a bulk acceleration. So the simulation stops at this frame, and only by looking by eye, you could sort of see that there are some difference in this cloud accelerated by cosmic ray and by hot wind. Probably the most obvious one is these clouds in the cosmic ray acceleration have generally lower density compared to the cloud accelerated by hot wind. And this can be confirmed if we look at the gas density distribution. So this, I'm showing the gas density distribution. The green dashed line shows the initial density distribution that's decided by thermal instability. So we have this cold dense gas that takes the majority of mass, and we have a hot diffuse background. And these two solid lines are from the acceleration simulations at a fairly later stage where they undergoing this bulk acceleration. So compared to the initial distribution, the cosmic ray actually decreased the density contrast a little bit, while the hot wind actually enhanced the density contrast a little bit. So we think this might be related to the fundamental difference mechanism for cosmic ray and hot wind to push this cold gas. So for a cosmic ray, unlike the hot wind, which just form a strong shock near the wind cloud surface, the cosmic ray actually can penetrate into the cloud slowly. And inside that cloud, we have a little bit extra cosmic ray pressure to support the cloud. And now we think that's a possible explanation for why we are seeing a more diffuse cloud in cosmic ray acceleration compared to hot wind. And I think this is interesting, especially thinking about in some context, cosmic hot wind kind of having trouble to produce a sort of multiphase outflow that has a too high density contrast compared to what line ratio observations suggest. So maybe adding cosmic ray will gearing things to the promising direction, but it definitely needs more investigation. And from here, one observation we can see is the gas property is definitely being modified during the acceleration. And how does that gonna affect our cold gas survival and acceleration? So next, we look at the mass evolution, which is in this upper panel, and the velocity evolution in this lower panel of all this cold gas. So for the velocity evolution, they both have a pretty linear acceleration, and the ending velocity, although there are some discrepancies, but it's not a huge offset, which is good because we intentionally try to control the momentum input from cosmic ray and hot wind to be similar. So if their density and mass are not too huge off, we probably should expect a similar velocity. But there is a significant diverging in the mass evolution. So in the hot wind case, the mass evolution is normalized to the initial value. So in the hot wind case, we have a cold gas mass growth. So this is good because if we plug in our parameters into the theoretical models based on what is a cooling time in the mixing layer, it tells us that we should expect a mass growing in the cold gas mass. So this roughly matches to what theoretical picture predicts, but what happened in the cosmic ray, why we got a dropping mass here. So I think to understand, so after this point, these are really work in progress, but I think to understand the cold gas mass evolution, we need to look at where does cooling and heating actually happens. So in this slides, I'm showing on the left panel the gas density. And I kind of want to point out that if you still remember the movie, we're actually doing this in a fairly long box. And you can still see a lot of cloud structure here, means that we are running them at fairly high resolution because we monitor our simulation to make sure the field length is always resolved to get a resolution independent result. And the field length is like the characteristic length scale where your cooling is balanced by thermal conduction. And it also kind of decides what is a cloud size after thermal instability creates this multi-phase gas. And on the right panel, I'm showing what is the actual amount of cooling and heating happening in this gas. So all the blue here means the gas is experiencing cooling, while the red here means the gas is experiencing heating. So the structure is also interesting, but it's similar than what thermal instability result looks like. Inside the cloud, both heating and cooling are relatively low because these clouds have temperature that near the temperature floor. But around the cloud, there's a thin cooling layer kind of protected this cold gas from a quick disruption. And around that cooling layer, there's a thin heating layer around it. So we could imagine there definitely mixing happens in this interface that we probably didn't really resolve. And one of the reasons we think we're getting a drop in the cold gas, in the cosmic ray acceleration, is because when we check how fast this cold gas can cool, which is a cooling time scale of all these gas experiencing cooling, we find that a key difference between hot wind acceleration and cosmic ray acceleration is in later time, the dynamics happens in the cosmic ray acceleration already modified the gas properties so that some of these gas, especially in this lower density region, they can no longer cool efficiently as initial value predicts. So that's why we start to get in dropping cold gas mass in the cosmic ray acceleration. So I'm gonna skip relatively fast in these few slides, but this is also just sort of the evidence of the statement I was saying. This is we're looking at what is the distribution of cooling time in those gas experiencing cooling. So roughly you can just take a look like in the cold gas. So the gray dashed line shows the initial value, but in the cosmic ray acceleration, now the distribution has been changed after the acceleration, and we get some gas that cools much slower compared to the initial value. So at least one conclusion we got for now is the acceleration or the dynamic process happens here actually modify the gas property. So if we only use the estimation based on cooling and mixing according to our initial value, we're probably gonna get a prediction that is different from what we're gonna see in simulation. So this is quite interesting to me because the first time I see that drop in cold gas mass in cosmic ray driving case, I thought, okay, this must be related to cosmic ray heating. But it's actually when I check the heating versus all this optical thin cooling, I find that the cosmic ray heating usually be 1 or 2 order of magnitude lower than the cooling. So they are not important in terms of energy loss or adding. But so for this non-thermal source, I even see something like similar than this in the previous radiation driven cloud case. So for this non-thermal source, when you have very efficient cooling, this source might not directly change the cooling and mixing by adding energy to the gas, but they kind of like triggering some dynamic process that modify the gas property and change the picture of cooling and mixing. So I'm probably going to stop here, but in the next few slides, I wish to very quickly go around some other components in our research project just to have an impression. So we also look at the gas density, the gas distribution, like where are these gas that experiencing cooling and heating in multiple phase space, like here is in temperature versus density, and here is in density versus the actual amount of heating or cooling. And we also have the suite of simulation with different magnetic field that you can sort of see here as we're lowering the field, we get a more turbulent behavior. Also the characteristic size of cloud formed in these different field strengths are also different. And even the density has somewhat difference. So how does that gonna change mixing and cooling? And then last, I'm showing a suite of simulation, which I like a lot because So in these simulations, we took a cloud that formed from thermal instability. It's irregular, it has some structure in it, and we put it in a uniform background, boost the resolution, and do a single cloud interaction simulation. So these are one way to serve as a resolution study to resolve any potential dynamic instabilities, which so far we haven't seen a lot here, but also it's good to compare with other works on this cloud crashing type of simulation. Like here is a irregular cloud being accelerated by the cosmic ray, and the same cloud accelerated by hot wind. And I even did a spherical cloud with comparable mass and size to this irregular cloud, but driven by cosmic ray to kind of answer my own curiosity, does shape really matters? So I guess I'm gonna really stop here, and that's all. Thanks for listening.
Thank you very much for this very nice talk. So do we have any questions? Yeah, Drummond.
Cool. So, I mean, so cool. I have like a million things I would like to ask you, and I'm so sad that we weren't able to overlap at the CCA more to talk about this while you were working on it. But I definitely, you said this and I missed it. Just to confirm, these are two-dimensional?
Oh, these are 2D simulations.
Yeah. Okay. And the other thing I was wondering, so let's see if I can actually phrase this into a question. The background medium is in thermal equilibrium for the most part. Is that correct? So you have like a bistable. Okay.
So I think there are still some low level of heating and cooling going on in those global simulations. But at least in these zoom-in simulations, we intentionally reset the heating rate to make them in thermal equilibrium.
Gotcha. Okay, just because a lot of the work that we've been doing on these turbulent rated mixing layers, both you know my group and other people, the background medium is not in thermal equilibrium. And in some simple experiments I've done where you have sort of an equilibrium, a background in equilibrium, it can change things a little bit. So maybe we can talk more about this later, but this is very exciting work.
Definitely. I also appreciate a lot of interesting conversations between us. I think some of conversation actually inspired me, like how exactly I should do this. And actually, I was reading some of radiative mixing layer papers done by group like happening here. I think that's the right direction to go to have a more consistent understanding of this type of multiphase and feedback interaction simulations.
I'm going to take us very much to the macro scale. Can you see the Zoom bar, or is that just what I'm seeing? No? Okay, great.
Yeah, you're good.
So yeah, I'm Lucia. I'm a 5th-year PhD student at Arizona State University and NASA Goddard. It was a true delight to work with Shai for the fall and really apply myself to working with simulations. And I also have to call out a lot of other folks at the CCA that served as mentors and also like crucial allies in this large project, specifically Austin Gibber-Pillai, who is applying to PhD programs soon, FYI. Paco, Rachel, and Daniel. It's really been a team effort, and I'm so thrilled that I was able to be a part of this. So I want to tell you about this new set of simulations that for now we're calling Camel-SAM. The name is up for debate and modification. But this is a new suite of simulations for machine learning, and specifically seeing how we can constrain cosmology using the clustering of galaxies. Cool. So the core question that the collaboration of camels is trying to answer is what summary statistics are the most informative to constrain and measure cosmology in observed galaxy surveys. So I guess like the 3 things that are driving this entire thing is, first of all, my specialty in measuring the clustering of emission-line galaxies that I brought to the CCA for the program. The recognition that neural networks are really powerful tools for finding patterns that might be hard for us to see. And also trying to find tools that might be able to constrain cosmology in galaxy formation and baryonic physics all at once. So the CAMELS project is super, super cool. You guys should, if you haven't read Paco's paper yet, you absolutely should. But the goal of the CAMELS project is to create theoretical predictions for observables such as star formation, rate history as a function of cosmology and astrophysics, and most importantly, create a data set for machine learning algorithm training. So the root core CAMELS project are simulations that are 4,000 in number. 2,000, half of those are dark matter only, and the other half are split evenly between state-of-the-art magnetohydrodynamic simulations run through either the TNG model or the SIMBA model. And these simulations are about 25 comoving megaparsecs per side. And they're really fine resolution, and they vary omega matter, sigma 8, and 4 parameters to control stellar and AGN feedback. So I specifically study the clustering of galaxies, and I wanted to see what we could bring to this. So clustering, for those of you who don't do large-scale structure, it's a really vital and common summary statistic that envelops not only cosmology, but baryonic and environmental effects. So when I talk about clustering statistics, the ones that I bring to the table and will be showing you are the 2-point correlation function that many of you will be familiar with from baryon acoustic oscillations, but we're going on a much lower scale and thinking about how dark matter halos are occupied by galaxies and taking advantage of the really robust theory that exists there. We can also look at count in cells, which literally drops a cell of a given size and counts how many galaxies are in there. There's a lot of information in that measurement, and we know from different papers that Paco has written and other folks like Cora Ullman that it can disentangle effects of like dark energy and other kind of cosmology. And the one that I specifically bring is the void probability function that simply asks, if you drop a circle or a sphere of a given size, how likely is it to be empty in your survey? And it's a very simple sort of statistical measurement that is a snapshot of the count in cells larger distribution. And it's very sensitive to number density, and we can use it as a really easy anchor to compare things. But the catch about clustering is that even in idealized simulations where you know exactly what went in, you need to have robust sample sizes to avoid that noise and large enough volumes to really trust the measurement at the radii you're making. So some of you might see where this is going and where it went in the fall. So we can look at the actual CAMEL set, right? These are 25 comoving megaparsecs. And in all these simulations, let me guide you through the plots. So the void probability function we measure as radius. What is the probability that it will be empty? So more clustered things have higher VPFs. The 2-point correlation function is often a power law. And then count in cells. In this case, I take a specific radius and we look at how the distribution of the cells and how many galaxies they have within them. So really, really clumpy distributions are going to be very much shifted to the left. And when we think about how we can leverage clustering measurements, don't worry too much about the details of these plots because we're going to move past them really quickly. We first ask, okay, are the signals that are being caused by the different cosmological parameters or the astrophysical feedback, is that signal going to be stronger than what happens just from cosmic variance? Because every time these simulations are run, they have a new random seed. So for example, with the figure on the left, the orange plot are the cosmic variance set, which were 27 simulations that had exactly the same parameters, but had different random seeds. And then the blue is the distribution of the Latin hypercube simulations, in this case, the 1000 SIMBA simulations that managed to pass, however many of them managed to pass a stellar mass cut. And we see that for different clustering measurements, you know, there might not be super constraining. For example, 2-point correlation function, cosmic variance seems to swallow a lot of that. The VPF and count in cells seem to have something in there. So maybe something can come with it. And also we can look at what's called the 1-parameter set, where the team held all but 1 parameter at a time at a fiducial value and then varied it to the extremes. And as we expect, omega matter, the density of matter in the universe, has a really, really strong effect in this case on count in cells. And also depending on whether it's a SIMBA or the TNG volume, maybe like one of the supernova parameters shows a lot. But part of the issue is that I was finding with the original CAMEL set is trying to get enough of the simulations to pass a really generous, simple galaxy selection. So for example, I just ask, I want star-forming galaxies. Some volumes get 4,000 of them, and some would get 60. And that's really difficult because we know that clustering measurements can get more information beyond just their number density. So if you try to correct down to number density, it gets really hard. But neural networks are smart. They can do a lot. For example, in Paco's, the introductory paper that Paco led for camels, they used a really, really simple neural network to try to see if they could measure the input astrophysical and cosmological parameters from the star formation rate history. And as we see here in my very rough recreation from 2 weeks ago, it does really well. Star formation history can predict both cosmological parameters and the supernova feedback. What about clustering though? You know, it does okay. So with the SIMBA simulation, for example, if I feed it stellar mass greater than 0 objects, omega matter comes through. Okay, this is great. This is super cool. But the other ones aren't really predicting. So for example, except for the signals we're seeing for cosmology, the neural network is predicting, the predictions are on the y-axis, it's predicting the mean. And the other thing, again, I mentioned that passing the selections is kind of a problem. In this really generous selection, I had 41 simulations that didn't make it through. And that's not too bad. But as we get into trying to create more robust things to feed our neural network, we need to make sure we maintain a really rich and large training set. And these are very preliminary results. So SIMBA did okay. What about TNG? It does not do well. If I try training the neural network on the illustrious TNG galaxies and their clustering, it doesn't really predict anything. So this is kind of a bummer. And we were seen signs of this in like October. So Shai and I had the wild idea. What if we did camels, but bigger? So this is how Camel Sam was born. So the key to this project is taking advantage of semi-analytic models that can paint galaxies on top of n-body simulations. And specifically, we're using the Santa Cruz SAM that Rachel Somerville has developed and that Austin Gabriel Pillai has tested very thoroughly in the TNG volumes. So this method of generating simulated galaxies is computationally so much faster than running the hydrodynamic simulations, of course, at the cost that you're taking these semi-analytic shortcuts. We have significantly smaller storage demands. It's also great for the team because we can add an additional model of galaxy formation to kind of throw at the neural network. It's really easy to rerun the SAM with new parameters once the merger trees are made from the n-body simulations. And this was good for me to see, and I did this with Austin. The SAM shows really consistent results in all of the TNG volumes and resolutions. So what we're doing so far, and if you're seeing me on the preempt queue, this is what I'm doing. We're aiming to run 1,000 dark matter only adipo simulations of 100 co-moving megaparsecs. If you take out the little h, it's a perfect 150. I think I'm 2 simulations away from passing all 400, and I think I've got 420 or so finished. And we're covering the same really wide cosmological range as camels, and we're adding in new feedback parameters that the SAM specifically has. So this is super, super exciting. So the first thing that I wanted to answer, what's my time? Okay. Before we started on this endeavor of hours, like many, many weeks of computational time, we wanted to check that this would work. So the first little example we did is we ran really, really big dark matter only simulations of 200 megaparsecs, or 300 if you take out the little h. We ran them at the extreme cosmology. So omega m is 0.1, which is really extreme, like we think it's 0.3. And then sigma 8 at 0.6, and then the very, very other extreme end, with the expectation that the clustering signals should show differences, and we see that. So this was very encouraging. Then we tried doing slightly smaller simulations. In this case, once you take out the little h, there are 100 co-moving megaparsecs. And we're seeing that the clustering signal is still showing what we expect, and that we're getting more galaxies. And just this week, I went through by hand, and I plucked out a few simulations that were really sitting at the very extreme ends of our parameter space to see what their clustering is looking like. And this is super preliminary and I think really exciting. So first of all, I can get 5,000 at least, if not 10,000 galaxies in every single volume. And that's really helpful if you're trying to do clustering measurements. I can be a lot pickier with my star formation rate cuts and my stellar mass cuts. I can do specific star formation rate. And we're seeing that at least, in this example, a star formation rate cut, we see really interesting behavior. First of all, we see the cosmological parameters separate out in a way we would expect. And also we're seeing that the feedback parameters, in this case, the supernova parameters that control mass outflow rates, can also affect the clustering, but that's okay. The great thing about having galaxy catalogs, if they're simulated, is I can try different cuts. So for example, if we do stellar mass, it's a different pattern than we saw before. So this is great because the neural network can just get all of this information and learn something from it. So this is super, super exciting. And this is how I feel about it. Yeah. So I hope you guys are also really excited about this. Again, the whole point of this project is trying to figure out what kind of power and how much constraining power clustering summary statistics can do with cosmology. And also, I encourage you to be creative with what you might be able to do with this many n-body simulations, right? We're gonna have 1,000, give me like 3 weeks. And right, these all have halo catalogs, merger trees. And part of what hopefully, I guess you don't really see in this is the huge amount of labor that went into creating this enormous pipeline. With a lot of help, a lot of folks like gave specific parts, and all together it's doing this. And so you're going to see it running, and hopefully this will finish in a few weeks. But yeah, it's a really exciting project, and I hope you guys stay tuned.
Thank you so much, Lucia, for the very nice talk. Really interesting stuff. I'm glad you mentioned the amount of labor, because for me, whenever I hear about this, I just get I start sweating a bit thinking about the data management challenges and everything. So I'm impressed with the people doing this. So we have a question from David was first.
So have you thought, or is anyone thinking about doing some of the kind of beyond 2-point statistics like void statistics and more power spectrum on this?
I know so power spectrum was done on the OG camel set. And that's something that's definitely accessible here. I do worry about doing I know when you talk about voids, you're talking about them as like cosmological objects and not the statistical things that I'm talking about, just for like other folks in the room. And I'm not sure if these volumes are big enough for that. That might be a thing to ask like you or Alice, who was just here. If you know if 150 megaparsecs is enough to be able to study voids as their own feature.
Well, a lot of them are a lot smaller than that. So, 100 megaparsec cubed simulation isn't, but you've got 1,000. So, right, this is really 3,000 megaparsec, the volume of the simulation is, 1,000 megaparsecs cubed.
Yeah, it could be cool. Maybe at a postdoc. Yeah.
I just wanted to know what you're doing that. And I guess the other question, this is being really greedy. Okay, you can run a SAM on this, and why can't you make your box even bigger?
Honestly, it was straight up the limits of my personal time and also just data storage at CCA. So right now, I've already gotten an email from Scientific Computing being like, hey, you're already at 80 terabytes. Can you please why? Please slow it down and move things to tape. So that was a big thing. So right now with this scale, the simulation, an individual simulation will take about a day to 2.5 days of real world time. Right. And just based on the amount of computing, just the queue, I can run on a good day, I can do 40. On days where lots of other folks are using it, it might be 10 at a time, just trying to get it in there. So that's really been the constraint. But we did definitely talk about it. At one point, Shanna would should we do 300? But
yeah, but at the end of the day, do you really need the full box, or do you want the galaxy catalogs, which must be much smaller?
Yeah, so the galaxy catalogs are much smaller, but we knew for sure that other folks would want to use the halo trees and merger trees. So I guess in the internal audience, I know what will be readily accessible on Ceph will be the halo catalogs, the SAM outputs, and then on tape are compressed snapshots. So folks who do want the full 100 snapshots of the dark matter simulation can talk to Shai about it.
Will has a question.
Yeah, I guess this is in some sense a follow-on to David, and less directly about what you're doing or even thinking of going to the power spectrum, but what kind of intuition should I have? Right now, your estimator, if you like, of the cosmological parameters is this very discrete, extreme value thing, right? Voids don't have anything in them based on your cuts. it's, you know, very discontinuous. How much information are you leaving on the cutting room floor by using that as your void estimator, rather than something that's smoother or examining, you know, different levels of emptiness and so on? Not even necessarily going to the power spectrum, but just like, you know, a little bit smoother.
No, that's a really good question. And there's a, yeah, so I know some folks have been doing like under density probability functions. I'm thinking of Jillian Belch-Morman did a paper recently. I went to college with her. That incorporated that and the void probability function. So yeah, there's always information left behind. The one really good thing about the void probability function, even though it is very, very stark, it does tie to the 2-point correlation functions and volume average redshift space. And most importantly, it is very, very quick to calculate, especially if you do like a nearest neighbor KD tree. And that becomes a real issue, especially, you know, if I'm trimming down 1,000 simulations to 5 or 10,000 galaxies each. I guess I'm thinking about it as like on the short term, you know, we're trying to keep this really ambitious project that is a little bit more constrained. But you're absolutely right. There's a lot of information in clustering statistics that can hold other information. But I would also argue that the void probability function will include some of the signatures that will come from ones that are a little more generous and like less stark.
Yeah, cool. Okay, thank you.
And then we'll take a final question from Sultan, please.
Yes, that's super cool. Yeah. So I wanted to ask, how do you like the new set of parameters? Is it similar to the camels exactly, like the velocities and the amplitude and like the feedback for the stellar and the AGN, or they are quite different?
We tried to get as close as we could. And I actually have like my notes that I took on this open just in case someone asked about it. So the supernova feedback ones, they're quite similar to the SIMBA parameters. So specifically, if you look, and I think it was the 2015 SAM paper that Rachel led, it's mass outflow rates. And in this case, our two parameters are the amplitude for that power law and then the slope. And then we did have to make some choices with the AGN feedback. Okay. So right now, the one parameter in there is, oh goodness, it has to do with like the radio jet feedback. And for now, we're only having one AGN parameter. But in the future, again, it's super easy to add more. But yeah, so just to start off, we have 3. But that's a really good question. And if folks have ideas about it, yeah, the SAM is also really different from TNG and the SIMBA models, like especially in the AGN. So yeah.
Yeah, it's because I would imagine there are a lot more parameters in the SAM than in these other simulations. So one might imagine varying more parameters than these, than only 6 parameters. Yeah, but this is very relevant to what we are trying to do now with the camels, because the size of the box now is much bigger. So I will look forward, like after you're done with running all this, yeah, let me know so we can maybe run because I'm interested in doing reionization with camels, and the small box size is a problem there. So I guess now it's very good we have this now. Yeah, thank you.
Thank you.
Okay, thank you very much, Lucia, and thanks to all of our pre-docs for these great talks. It's nice to see so much interesting research that was done during your time at the CCA. Thanks to everyone for attending this symposium. And as I said at the beginning of the time, I hope to be able to meet you all in person. Definitely come back and visit, reach out to your mentors to come give a talk or just say hello. So thanks everyone and have a great weekend. Bye.